We are talking about design assisted by numerical simulation. This is recent, this is not unknown and not new, but I would say application of numerical methods in design practice are relatively new. And the main point was that there was lack of safety concepts which can be applied and which will be harmonized with present practice and will be also in the codes. So I show a few examples. For example, the buildings where we have some advanced or complicated problems. It can be composite structures where we have steel and concrete elements in complicated situations. Very nice and typical application is in wind turbines, where we couple the steel parts using grouts, which is concrete, and hydro plants, so plants providing energy for water. So these are usually very huge structures, or even skyscrapers 600 meters long, which can be today handled in a full nonlinear analysis. Or I show you example from nuclear power plants, where we can do pushover analysis using full 3D models. So I would say this is the current situation. It has been, there is quite a demand in practical world for these applications. But I would say I'm a little bit skeptical about application of solidly based safety formats, because I'm closely following, for example, development of Eurocodes, and they very much prefer simplified approximations for safety. So if you talk about sampling methods and response surface methods, it is still difficult that engineers accept it, from very simple reason, because they are prepared to run 1 or 2, maybe 5 analyses, but not hundreds. So even though I must say today, even running such a large problem like this one with millions of degrees of freedom, it's not a big deal actually. If you use parallel computing, distributed processing, it can be done. But anyway, people want to behave in an economic way. So I will just describe the framework of the safety which we present use. In practice, I would say, maybe not in your world of mathematicians and reliability people. First of all, we simplify our design condition. So we separate the action and resistance or performance. So it is easier to distinguish about uncertainties. And furthermore, we may do very simple model where design resistance is mean resistance by applying the safety coefficients. So this is basically framework we use. I would say our resistance in this case is the resistance obtained by simulations. It can be very general. It is usually a vector, many dimensional, and so on. Sometimes it is one variable. And of course, when we talk about safety factors, we have it is practical also to make distinction between safety, which can be described by a probabilistic analysis, very simply, like material variability, geometric variability, the so-called random variables, which are easily recognized and easily applied. And we know how to do this. I think at least the advances describing random variability of our world is relatively well known. But there is another problem, and it is uncertainty involved in models. And especially if you talk about finite element models, they are very complex and they should be very uncertain. So it is a really problem. So what I'm going to do today, I will talk only about this effect, the effect of model uncertainty. And it will be very simple, actually, what I will show you. So we define the model uncertainty as a ratio between test results and simulation. So this is clear. It is very direct reference to testing. And if we make a number of these evaluations, we obtain a database which describes this behavior of our model. First, we are talking about uncertainty which is based on knowledge. This is lack of knowledge. Are we modeling correctly or not? We don't know anything about details. We can speculate. Many people define exactly what is uncertain in model, but I always doubt about it, because I think it can be in finite elements number of things. But first of all, these are the constitutive models, for example. We base it on fracture, on plasticity, and then we have finite element model which is sensitive to discretization and so on. Anyway, what we decided, and I should have said that all this effort is driven by our technical and commercial activities. We develop software Athena, we want to provide it to users, and we want to tell them how safe it is, how reliable it is, and so on. And we tell them how to assess the material uncertainty, which has more or less nothing to do with the model. But we have to tell them how is our model uncertain and how it contributes to reliability. Okay, so I would say what I will show you, I will generate a group of these results, and then I say, okay, we assume that this is random. We assume even what is the probability density function, but it is not necessarily the same function. You can choose anything which fits best to the results. And we sometimes should consider if we have large database or small. In this case, we assume log normal distribution, and it is based on the mean uncertainty from this database and coefficient of variability and some application of some coefficients. So I'm talking about this group of tests. We have 33 cases, punching shear test. We have shear strengths of beams, basically large beams, and we have bending of normal beams to describe also the usual design situations. And the range of parameters is rather large. You see we have brittle modes of failure, ductile modes of failure, with and without shear reinforcement, also in brittle modes of failure, concrete, higher strengths, normal strengths, and most important, the size effect is there. We have in this database of 33 cases, we have sizes from 0.1 to 4 meters. So the scale is 1 to 40, which is, I think, very important. And all the analyses are done by our nonlinear software Athena. So just briefly going through the tests which were used. This is test of Aurelio Montoni, different sizes of planes, slabs in punching, without reinforcement. This is the result of simulation. In this case, you can see how it works. We always try to make a simulation which can distinctly show peaks, indicating the resistance. These are the descriptions of failures. In this case, rather coarse mesh. It is not research. It is oriented to design situation, more or less. So we have some punching cones here, like in tests, and here. And these are two slabs with different sizes again. And this is description of compressive failure, which occurs in punching, of course. And this is very interesting subject. So we are now talking about shear of beams, shear failure of beams. And I'm starting with the largest beam, which has, I think, ever been tested. It is tested in Toronto by Michael Collins, which is here. And they tested a series of beams with similar and different reinforcements. And you see, for example, in this case, this beam and this small beam are nominally identical, have the same reinforcing ratio, and have the same shear span. So it was very, very interesting. By the way, in the whole series, which I'm talking about, 33 beams, the simulations were done with knowledge of results, which is, of course, nice. And so we are removing uncertainty due to human, okay? Who may mishandle this, who may have funny approaches and so on. Except of these two tests, these were done as predictions. So we have also predictions. So this is the test, just you see, quite interesting that in order to save resources, they make two tests with one beam. So first of all, it fails in this weak span. When it fails, they repair it and load it again, and then they test this one. Okay, so, and in this series we have three sizes, 300 millimeters, 2 meters, 4 meters. Okay, so here are again, these are the predictions, you know. It's really surprising how good it was, and there was 66 people in the world trying to predict this. I'm humbly saying we did the best prediction, but it was not easy actually. Okay, so you see this is crack pattern, experimental, simulated, and the other one is tensile failure, more or less, and the other one is tension compression failure. And now I come to the third class of problems, which are beams tested in Torino, different sizes again, different reinforcing ratios, simulations of ductile behavior, simulation of brittle failure, and in this case the brittle failure is compressive failure of concrete. I have always difficulties to push the run button. Okay, now I'm coming to results. So I think the most interesting result of this is that we have interesting information on mean fit of model and experiments for punching separately, for shear very close to 1, and for bending, which surprisingly has the largest distance from a mean. Interesting is that only bending is underestimated, and these two means overestimation. And then overall, in one group, statistics shows this fit and coefficients of variation. Having these informations, you can already start your some reliability concept and reliability analysis. For example, if we assume log normal distribution for resistance, and we can calculate this safety factor, assuming alpha and beta, reliability factor and coefficient for reducing down to resistance, and then we can offer these safety factors, and as a main number here is 1.16, which can be now proposed as a model uncertainty format for Athena only, and for the class of problems described by the ranges I have indicated before. So this is closing the part related to ultimate limit state strengths, and I will show you very briefly a few examples. I have already said this, and very briefly, another consideration, another study for serviceability states. So we say, okay, we are trying to investigate relation between modeling crack width and experimental crack width. And this is model uncertainty, and it is for crack width only. And the interesting difference with respect to strengths is that these are serviceability states. So up to date, the concept for design is that we work on the mean. So we should be actually focusing on mean, which is reliability factor 1. We want to see mean results. Unfortunately, concepts in codes are streaming for maximal cracks, and then it makes all these evaluations more difficult. Anyway, what I will show you how we came to model uncertainty factor for mean and variability coefficient of variation from 4 tests. 4 tests like this with different reinforcing ratio, different concrete cover, and these are the experiments, and I may show you what we do in simulations. And in simulations, this is based on fracture mechanics. There is no probabilistic approach whatsoever involved, and we get we have a region with a constant moment, no imperfection, so we should get actually uniform distribution of cracks, which is not the case, and I can talk about it why, but anyway, it is purely numerical actual reason. If we do very good analysis, we have almost regular distance of cracks and nice crack width and so on. And also, what is very important here, we have to work with bond, you know. So this is low displacement diagram at this point, which is approximately serviceability level of design. And you see that we have cracks. We can determine crack because it is localized strain. And we have also bond distribution here, very nice. So we have been comparing this, of course, with the code model, which have the only difference in code model is that they assume constant bond here, and they assume nothing about crack width. They just transfer the deformations along the bond, and that is the crack width. So I don't have time to go to comparison between design based on the engineering concept and this one. There are large differences, by the way. Anyway, these are the results. I don't go to details, but what we found, that the mean fit for average crack is quite nice. It is 10% underestimating, which is not so bad, because if you compare the same thing with engineering codes, you are even much below. But what is disturbing, that the experimental crack width for a maximum crack we don't cover correctly, so we have to do something about this. So this is just only for beams. I think from the point of view of validation, it is nothing. But it is a starting point. We are doing, we have colleagues in other laboratories. They do a lot of nice experiments, and we would like to extend this study, first of all, to capture correctly mechanics of crack spacing and bond and so on. And although our present model indicates it is quite good, and then the prediction of cracks is in average quite nice, but it has to be validated in similar manner as we did for ultimate limit strengths. Okay, I think that's it.